Manolescu from Stanford University. Professor Manolescu is a recipient of the Frontier of Science Award this year, and he's a leading expert in low-dimensional topology, gauge theory, and Floer theory. Using Seiberg-Witten Floer homotopy theory, he disproved the long-standing triangulation conjectures in high dimensions. So the title of his talk is Triangulations of Manifolds. Let's welcome.
Thank you very much. I would like to thank the organizers for inviting me to speak here and for the award. It's a pleasure to be here. So here is the plan of the talk. I will first talk about the motivating question, the triangulation problems for manifolds. Then I will explain how they can be boiled down to questions in 3+1 dimensions. So the original questions are in any dimensions, but in the end you can reduce them to something just about 3 and 4 dimensions, questions about homological bordism. And then I will explain the disproof of the triangulation conjecture, which was previously reduced to something in 3+1 dimensions, using some tool called pin2 equivariant Seiberg-Witten Floer homology that I developed for that purpose. And then finally, well, this is some older work from 2013, so I figured I should talk about something new. So what happened since then? Well, this tool evolved into another tool that's more useful in other contexts called Involutive Heegaard Floer homology, and I will describe a few other recent results in low-dimensional topology using Involutive Heegaard Floer homology. Okay, so what is a triangulation? You can define it for any topological space. It's a homeomorphism from X to a simplicial complex. And let me remind you that a simplicial complex is some space that's described by a finite amount of data. You have a set of vertices, and you need a set of simplices, which is just a set of subsets of S, such that whenever you have a subset sigma in there, then you also have all the subsets of sigma. So for example, here is such a collection of subsets of 1, 2, 3, 4. Every vertex gives us a point, and then we have an edge whenever we have a 2-element subset, and a triangle whenever we have a 3-element subset, and then you can build tetrahedra and so on. So that's a simplicial complex. And here is a triangulation of a torus. So the torus can be triangulated. You can break it into triangles, but if you break it only up to the third square there, then those have the same vertices. So the triangles have to be determined uniquely by the vertices in order to be given by a simplicial complex, but you can just break it up some more into more triangles, and then each triangle is uniquely determined by the 3 sets of vertices. So then you can say you triangulated your space, and this allows you to study the space combinatorially. You just have a finite amount of data, maybe you can plug it into a computer and get information about the space. So that's a nice thing to have. Okay, so what spaces we study in topology? The most popular ones are manifolds, and there are 3 kinds of manifolds that topologists study. Topological manifolds, which are just spaces that locally are like Rn. So the transition functions, you don't have to define them, but they're just continuous. Then the smooth manifolds, where the transition functions between different charts are smooth, C infinity. And then there's piecewise linear manifolds, where the transition functions are piecewise linear. You have Rn, and you break it into simplices, and you want on each simplice to be linear. So you can define these 3 notions of manifolds, and you can ask if those kind of spaces can be triangulated. And there are also, for manifolds, there is a particularly natural kind of triangulation you can request, which is usually called, the traditional name is combinatorial, but really it should be called PL, so I'm going to use this name. And that's the kind of triangulation where where the link of every simplex is basically a sphere. It's piecewise linear, homeomorphic to a sphere. What is the link? The link is, you look at this vertex here, and you look at all the simplices that contain it, and you take the boundary. Okay. So if the link is a sphere, then locally the space looks like the cone on a sphere, so it is a manifold. Yes, question. It has to be piecewise linearly homeomorphic to the sphere, yes. Oh, there's no, I'm just thinking of it as, it could be, um, any kind of triangulation, but basically I'm just thinking of it as a PL space, yes, and then I want PL homeomorphism. Yeah, okay, so these are natural triangulations on manifolds, and people sometimes just focus on this kind of triangulations. All right, so what do we know? So the simplest question was asked by Poincaré in his analysis situs. He defined manifolds, and he asked, well, in modern language, you can rephrase his questions as, does every smooth manifold admit a triangulation? And it turns out the answer is yes. It took some time for people to prove this rigorously. So Cairns and Whitehead around 1940, they showed that it's true. So in fact, every smooth manifold is piecewise linear. And once you get to piecewise linear, you can triangulate it. But the much harder question is about topological manifolds. So this was first asked by Kneser in 1924. Yes, does every topological manifold admit a triangulation? And the reason why it's hard is, well, in the smooth category, smooth maps can be approximated by definition. They're differentiable, so they can be approximated by linear maps. So you expect that everything smooth can be made linear. But topological manifolds, where you just have continuous maps, and how do you approximate them by something linear? That's harder. Okay, and there are two variants of the question. You can ask, do they have any triangulation? Or you can ask something stronger, do they have PL triangulations? Okay, so it's not immediately clear that manifolds can have non-PL triangulations, but they can. So here's an example. You need to start with a homology sphere with non-trivial fundamental group, like you can take the Poincaré sphere. It's a famous example. So homology sphere means a manifold with the same homology as the ordinary sphere. The first such example is in dimension 3, the Poincaré sphere. And what do? You take the suspension of it. So you take two cones on it. All right. And then you take the suspension of the suspension, so a double suspension. Okay, now it's non-trivial to show that the double suspension is actually homeomorphic to the sphere of dimension 2 higher. This is not true for the suspension itself. Well, it's not true for the suspension itself because because locally near this vertex, if you just look at the red part, the complement of a neighborhood is not simply connected. Sorry, if you look at the neighborhood and take out a point, that looks like M, and it's not simply connected. Whereas for the ordinary sphere, it's just the sphere. It's simply connected. Okay, but if you do the double suspension, Edwards and Cannon, that's a deep theorem. They prove that this is a sphere. It's Sn plus 2. And if you triangulate your original M, and then you take cones on this triangulation and then cones one more time, then you get a triangulation of the Sn plus 2 that's not PL. And it's not PL because if you look at the link of this vertex, the link is this red part, is the first suspension. And the first suspension is not a sphere, it's not even a manifold, in fact. Okay, so manifolds can have also non-PL triangulations. Okay, so what do we know? So it's actually easier to just focus on PL triangulations first. Let me mention what's known there. So in dimension up to 3, the manifolds have unique, smooth, and PL structures. And in dimension greater or equal, so they have PL triangulations. In dimension greater or equal than 5, there was work of several people in the 60s, and they showed that there exist manifolds that are not PL. So they don't have PL triangulations. In fact, I forgot to say, but basically having a PL triangulation is the same as being a PL manifold. That's not too hard to show, but it requires some thought. So yeah, so they showed that there exist non-PL manifolds, and they gave an obstruction, this element delta of M. It's called the Kirby-Siebenmann invariant that lives in H in the fourth cohomology with Z-2 coefficients, and the element is 0 if and only if the manifold is PL. So they showed exactly which manifolds are PL, and they also classified how many PL structures there are. They showed that they're classified by elements in some cohomology group as well. And since this cohomology group can be non-zero, they show that there exist PL structures that are not equivalent. And you can think of it as there are triangulations that are not equivalent even after subdivision. And this was another famous conjecture, the Hauptvermutung. People thought that if you have any two triangulations of the same space, you can subdivide them, and then they become homeomorphic. But that's not true. It follows from this. And in dimension 4, again, such things exist. So in dimension 4, the smooth category and the PL category are the same. So smooth structure is the same as PL structure. And by the work of Donaldson and Freedman in the 80s, it turns out that also in dimension 4, there exists non-PL, non-smooth manifold, topological manifolds, and also smooth structures may not be unique. That's the whole story. Okay. All right, so now we can ask about arbitrary triangulations. Do topological manifold admit arbitrary triangulation? I mean, maybe they don't admit PL triangulations, but do they admit any triangulations? And the answer was given first in dimension 4 by Casson, who showed that the famous E8 manifold of Freedman is non-triangulable. And then this left open the case of dimension greater or equal than 5 that I'm going to talk about. Okay, so I said that we're going to reduce the problem to something about 3 plus 1 dimensions, even though I'm talking about manifolds of dimension greater or equal than 5. So the way to do that, I mean, this was done in the 70s. The idea is that to study triangulations of manifolds, you look at the links of simplices. So if you had a triangulation, you look at a simplex, and you look at, again, all the simplices that contain it, and you take the boundary of that. That's called the link. That's kind of a picture of a link. If you had a vertex, remember it was something that looked like a sphere, usually. And in general, this also looks like spheres. You can show that they are homology spheres. They have the same homology as the sphere. So the links are homology spheres, and basically it turns out that you can rephrase. I mean, it's a whole theory that I'm not going to talk about due to Galewski-Stern and Matumoto from the 70s. But they rephrase all the questions about triangulations in terms of a group made of homology spheres. Okay, so let me tell you what this group is. It's called the homological bordism group. Okay, so the homological bordism group, there are different versions. I'm going to talk about the PL version. So it's made of PL manifolds with the homology of the sphere, the same homology up to some equivalence relation, where two manifolds are equivalent if they bound a cobordism, so manifold one dimension higher, which I drew here as a W. It has one boundary at y0 and one at y1. Also, everything is oriented, and this is a homology cylinder in the sense that the relative homology of W with respect to either boundary is 0. So homologically, it looks like a cylinder, and the boundaries look homologically like spheres. Okay, so you can look at all homology spheres divided by this equivalence relation. Okay, this is an abelian group. Their addition is connected sum. The n-dimensional sphere is the 0 element, and minus is changing the orientation. Okay, so what is it? Oh, by the way, so an element is 0 if and only if it bounds a homology ball. The element is equivalent to the sphere. Okay, it's an interesting group, but it turns out that, well, the work of Kerver in the 60s showed that this group is 0 for n different than 3. So, yes, once you encode this in this group, it turns out that you only have to, again, the group comes out naturally in triangulation questions by links of simplices, and this tells you that you only have to care about the links that are in that are three-dimensional, in other words, links of simplices of codimension 4. Okay, so just the third group is interesting, and why is it? That one is actually non-zero. So, why is it non-zero? This comes from a famous theorem in four-dimensional topology due to Rokhlin. Okay, so let me explain it. Let's say that we have a four manifold that's smooth, closed, and spin. It has a spin structure. Then you can look at its intersection form on the second homology. And, okay, just a second. I'm having a problem. Oops, sorry. Okay, I don't know what number slide I'm on, but all right, we'll just see how it goes. Okay, so the second homology has the intersection form, and being spin implies that this is even. Okay, so you can consider its signature, the number of positive minus the number of negative eigenvalues, and you can show using number theory that it's divisible by 8 because it is even. So this is a form over Z. It's a bilinear form on an abelian group over Z. But what comes out of topology, and this is Rochlin's theorem, is that, the signature is divisible by 16, not just by 8. Okay, so now if W is as above, but instead of being closed, the boundary is a homology sphere. So you have some boundary, which is a homology sphere. Then you still have an even form, and number theory tells you that it's divisible by 8, the signature. But now the signature could or could not be divisible by 16. What you know is that sigma over 8 mod 2 doesn't depend on W, it just depends on Y, on the boundary. And that comes out of Rochlin's theorem, because if you had two different manifolds, four manifolds with the same boundary Y, you could put them together and the signatures add up and they're divisible, the sum is divisible by 16. So the value of sigma mod 8 is just mod 2, just depends on the 3 manifold. So then we get an invariant of the 3 manifold, which is the Rokhlin invariant, or the Rokhlin homomorphism. It turns out it descends to a map on this homology cobordism group, theta 3z. It's just the signature of divided by 8, the signature of a 4 manifold with boundary that Y. You take that mod 2. Okay, so you can show it's well defined, and you can show that it is non-trivial. So for S3 you get 0. This is basically Rochlin's theorem. But if you look at another, at some other homology spheres, for example, the Poincare sphere that I mentioned before, the Poincare sphere bounds something called the E8 plumbing, and the E8 plumbing has signature 8, and you divide by 8, you get 1, which is 1 mod 2, so you get that this group has non-trivial homomorphism to Z mod 2, and therefore it's non-trivial. Okay, so this is an interesting group, and as I said, basically all the questions about triangulations of high-dimensional manifolds boil down to understanding this group. So let me be explicit about that. Here is what Galewski-Stern and independently Matumoto proved in the 1970s. They first discussed the existence of non-triangulable manifolds. So they said that non-triangulable manifolds exist in dimensions greater or equal than 5 if and only if this exact sequence does not split. So what is this exact sequence? You look at the Rokhlin homomorphism from theta 3z to zima 2, and you look at its kernel, and splitting would mean that you have a map the other way from zima 2 to here, that it would split as a direct sum of zima 2 and the kernel. And basically you would want to have an element that is 2 torsion, an element in here, the image of 1, that's 2 torsion, and it has Rokhlin invariant 1. Okay. All right, so what I proved in 2013 is that it doesn't split. So such an element does not exist, and therefore non-triangulable manifolds do exist in dimensions greater or equal than 5. So I will say some words about how to do that. But let me also discuss the other questions. Okay, so maybe this tells you if non-triangulable manifolds exist. You could also ask which ones are triangulable. And they show that they are triangulable if and only if some obstruction class in the fifth cohomology is 0. The fifth cohomology with values in the kernel of mu. This is an index 2 subgroup of theta 3z, so it's a pretty complicated group. But it's interesting that a short argument says that you can replace it by a simpler obstruction, that this obstruction is equivalent to 1 just in the fifth cohomology with z coefficients. If you knew something extra, that theta 3z had no torsion with mu equals 1. Okay, and that's an open problem. That's still an open problem. So I proved that there is no 2 torsion with mu equals 1, but in principle there might be 4 torsion or 8 torsion elements. Okay, but so that's why it's still interesting to study this theta 3z. Like it will tell you something about which manifolds are triangulable. And finally, you can ask, well, if it is triangulable, how many triangulations does it have? Up to some notion of equivalence called concordance, and they show that they're classified by elements in H upward 4, with again the fourth cohomology with values in this kernel of mu. So even if you do the second part and you show that the obstruction is in H upward 5 and Z, how many they exist, you kind of still have to understand this group, kernel of mu, which basically is the same as understanding this theta 3Z, more or less. So yes, so that's why the homological bordism group is important. Okay, so now let's talk about the methods for studying theta 3z. So theta 3z is about homology 3 spheres and cobordisms between them, which live in 4 dimensions. So this is a question in what people say 3+1 dimensions. And okay, so the way I described it was all about triangulations and PL structures, but in dimension 4, PL is the same as smooth. So PL structures are the same as smooth structures. So we can just think about smooth cobordisms. And smooth 4-dimensional manifolds are studied using gauge theory or symplectic geometry. These are the main methods. So there are 3 major theories that people use in 4-dimensional topology. There's Yang-Mills theory. This was the one that was pioneered by Donaldson. There's Seiberg-Witten theory, and there's Heegaard-Floer homology. Okay, so the first theory that was used to study, again, I mean, it did many other things, but we're going to focus on the homological bordism group, was Yang-Mills theory. So the Yang-Mills equation is a nonlinear PDE. It's elliptic modulo gauge group. It has a gauge symmetry. And Donaldson showed that it's sensitive to the smooth structure in dimension 4, meaning that the space of solutions on a 4-dimensional manifolds depends on the smooth structure on that manifold. And using the Yang-Mills slide, I'll just list some results that people proved. So Fintuschel-Stern and independently Furuta in 1990 they showed that theta 3z has a z infinity subgroup. So before that, all that was known was that there was a non-trivial homomorphism to Zima2, the Rokhlin homomorphism. Okay, so it could have been Zima2, but they showed that this is actually a big group. It has a Z infinity subgroup. Now you can ask, what about a summand? So for example, well, Q has a Z subgroup, but it doesn't have a Z summand. So having a summand is more information than just having a subgroup. And Freushow in 2001, he showed that it has a Z summand, just a Z summand, using also Yang-Mills theory. And then you can ask other things about the group. For example, which is it generated by some simpler three manifolds? So it's a group made out of all three manifolds with H1 equals 0. But okay, do you need all three manifolds? Like, can you just think about ciphered fibered spaces? That's a nice class. So Freushow proved that no, you can't. You need that there are elements that are not representable by ciphered fibered spaces. Another nice class of manifolds is surgeries on knots. Every three manifold is surgery on a link, but not all of them are surgeries on a knot. And you can ask, does it suffice to just use surgeries on knots instead of all three manifolds? And again, Nozaki, Sato, and Taniguchi, well, 5 years ago, they showed that there exist elements that are not represented by surgeries on knots. And Daemi, in 2019, he showed something about if you have a homological bordism between homology spheres with Rokhlin equals 1, then that cannot be simply connected. So people are also interested in simply connected homology cobordisms. But these are just some, a variety of results, and they were all obtained using Yang-Mills theory. So it's still an active area of research. Okay, but then the next tool are the Seiberg-Witten equations. This came as some sort of replacement for Yang-Mills in the 90s. So they're a system of two nonlinear PDEs, again elliptic, modulo gauge, and they're sensitive to the smooth structure. They're somewhat easier to study than Yang-Mills. Okay, and they have some symmetry. They have an S1 gauge symmetry, but they also have an extra thing, a conjugation, which I denote here by J. And if you combine the S1 and the J, you get two copies of S1. You get a group called PIN2. It's some subgroup of the quaternions. You can think of it's S1 union JS1 inside the quaternions. So the equations are naturally symmetric under this group. Okay, so what do you do with these equations? Well, you construct some invariants, and in dimension 3, you get something called Seiberg-Witten Floer homology. Let me just say it's an algebraic gadget. If you haven't seen it before, it's an algebraic gadget that encapsulates the solutions to these equations. It's an abelian group. In fact, it's a module over some ring. And originally, people just looked at the S1 symmetry. So there's a book by Kroheimer and Mrowka and alternate constructions by Freushow, Marcoli, Wang, and myself. And now, once you have this group, you can construct a homomorphism from the homological bordism to Z. This is called the Freushow homomorphism. So the idea is you have this Seiberg-Witten Floer homology of Y. This is a module over the equivariant homology of a point. F is just a field. And if you look at the S1 symmetry, you look at the S1 equivariant homology, which is F of U. It's the cohomology of CP infinity. And you can show that the Floer homology looks like a free part. There's just one free part if you're on a homology sphere, if that three manifold is a homology sphere. And then you have some torsion part over this ring F of U. And it has a natural grading, and you just look at the grading of this of the free part. So you extract one number. Oh, okay, it does some complicated story using the Seiberg-Witten equation, but in the end you get one number, and this gives you a homomorphism from theta 3z to z. Okay, just like Rokhlin was giving you a homomorphism to Zima 2. And once you have a homomorphism, well, you need to have some element that maps non-trivially. If it's 0, it doesn't help, but you can compute it for the Poincare sphere. You get that it has value 1. And therefore, it's an epimorphism. And once you have an epimorphism from an abelian group to Z, it means that the abelian group splits off a summand of Z. It splits off as the kernel of the homomorphism and the thing generated by P, your favorite, the thing that maps to 1. Okay, so this is how you can show that this has a Z summand. So this was done by Freud. I mean, he did something similar to using Yang-Mills, but you can also do it using Seiberg-Witten. Okay, so what I did was I looked at pin-2 symmetry, and I constructed things similar to the Freud invariant, but using equivariant Seiberg-Witten Floer homology with this group pin-2. And this has a more complicated structure. It lives over H, the cohomology of the equivariant, the pin-2 equivariant cohomology of a point. And instead of one map, you get 3 maps. They're not homomorphisms, but instead they have this property that they reduce Ma2 to the Rokhlin homomorphism. So the previous one, the Freud one, didn't have a connection to Rokhlin, but these ones do. And even though they're not homomorphism, at least they behave nice, or at least beta behaves nicely with respect to negation. Beta of minus y is minus beta of y. So once you have these maps, the corollary is that there is no 2 torsion in the homological bordism group with Rokhlin equals 1. Okay, so the proof is just that if there was some y, 2 of y equals 0, implies that y is equivalent to minus y, and therefore beta of y is beta of minus y. But by this property, you get that beta of y has to be 0. And then beta Ma2 is mu, so mu is 0. Okay, so mu cannot be 1 for a 2 torsion element. And this was what, by the previous work from the 70s of Galewski-Stern and Matumoto, this implied that non-triangulable manifolds exist in dimensions greater or equal than 5. Again, it was known in dimension 4. Okay, this still leaves some open problems. So we don't know what theta 3z is. In particular, we don't know if it has any torsion at all. It could be isomorphic to just z infinity. And one important question is whether you can find a homomorphism to Z that lifts the Rokhlin invariant. So my map was lifting Rokhlin, but it was not a homomorphism. The Freud map was a homomorphism, but it wasn't lifting Rokhlin. If you had some map that does both, then you could show that there is no torsion of any kind with mu equals 1. It's simple algebraic argument. And then this would imply that you could tell which manifolds are triangulable if this obstruction in H upper 5 vanishes. Okay, so that's still an open question. Okay, so since then, right, let's see. Yeah, I have 10 more minutes, so I want to talk about a different theory, involutive Floer homology. So this is some sort of offshoot of pin-2 equivariant Seiberg-Witten Floer homology, and it has less information, but it's more computable. So it's not sufficient to reprove the triangulation conjecture, disprove the triangulation conjecture, but it has other applications. So it came out of the same circle of ideas. All right, so let's see. So first of all, let me tell you about Heegaard Floer homology. This is some collection of invariants developed by Oshvat and Sabo around 2001. It uses symplectic geometry, Lagrangian Floer homology on symmetric products. There are some invariants associated to 3 manifolds, and in fact they're the same as the Seiberg-Witten Floer homology. This wasn't clear initially, but later it was proved by 2 independent groups of people. Yes, combining work of many other people, but yeah, so there are some versions. There's a non-equivariant version and an equivariant version. And okay, so why do we need this theory if it's the same as the old one? well, the way it's defined, it's more computable. It's somewhat easier to count holomorphic disks in symplectic geometry, and in fact, building on that, you can show that it's algorithmically computable. There are algorithms for computing it for any three manifold. Well, the first one was due to Sharkar and Wang, and then with Oshbart and Thurston, we also built one for the equivariant version. Yeah, so it has a lot of applications. You can recover a version of the Freushoff invariant delta, so you can reprove that theta 3z has a z summand. So once you know that there is this theory that's kind of like Seiberg-Witten but more computable, the natural thing is to try to do the pin-2 symmetry. And we're not fully successful in this regard, but in joint work with Kristen Hendricks, we built something like that called Involutive Floer homology, which takes into account the conjugation symmetry. There's also some conjugation symmetry on Heegaard Floer complexes, kind of like the J, and we get some groups called Involutive Floer homology. And the conjecture is that this is a Z mod 4 equivariant Seiberg-Witten Floer homology. So in pin2, we have pin2 is 2 copies of S1, but you can also look at the Z mod 4 in it, which is 1, I, J, and K, the quaternions 1, 1, I, minus 1, and minus I. No, let me try again. 1, J, minus 1, and minus J. That's the Z mod 4 subgroup. Yes, okay. So yeah, right. So this is some sort of replacement for the pin2 symmetry. So we had the idea that it must be useful for something. It must go beyond the usual Heegaard Floer, but still be computable. And indeed, we get some invariants, some versions of the Freushoff invariant. So we get some new information about homological bordism. And it's much more computable than the Seiberg-Witten versions. We can compute it for ciphered fibrations, for surgeries on many classes of knots, like torus knots, alternating knots, and connected sums of those. So this is some joint work with Hendricks and Zemke, and also work of Zemke, and work with Dye and Staffragan, Hendricks, Ham, Staffragan, Zemke. A bunch of people, they really developed this theory and made it computable for many classes of naturally occurring three manifolds. Okay, so let me tell you some, so the first applications were some constraints on which manifolds are homological bordant to each other. Once you have these maps, and if you have some invariant, and you have two manifolds on which the invariant take different values, you can say they're not homological bordant. So initially we had some small applications like that, but then people really got into it, and I want to tell you about what applications they got more recently. So I think I'll talk about 3 applications. Yes, I have like 2 minutes for each. Okay, so one is a theorem of Dye, Hong, Staffragan, and Chuang. They show that theta 3z has a z infinity summand. So previously, I said it was known already from Yang-Mills theory that it has a z infinity subgroup and that it has a z summand. So it was natural to expect that it has a z infinity summand, but yeah, it took 30 years and finally it was proved using this involutive version. And they, all right. Oh, that's another one, slightly different group of co-authors, Hendricks, Ham, Staffragan, and Zemke. They show that it's not generated by ciphered fibrations. So ciphered fibrations are a simple class of 3 manifolds. And previously, Freushoff showed that there exist elements of theta 3z that are not representable by ciphered fibrations. Okay, but, oh, and by the way, by contrast, it was an old theorem of Meyer's that every element can be represented by a hyperbolic 3 manifolds. So hyperbolic 3 manifolds are a more complicated class, and they represent all the classes in theta 3z. But ciphered fibrations, they can't represent everything, and they prove this. They show that they can't even generate everything. So there are elements that are not representable by any linear combination of ciphered fibrations. Okay, next, what do we have? Okay, here's an application to knot theory. Here is a knot. This is called the 2-1 cable of the figure 8 knot. And an important question in knot theory is which knots bound disks in 4 dimensions. So
Topologically slice or smoothly slice?
Smoothly slice. Yes. Yeah, I think the topologically slice is still not known. Yes. Yeah, so in knot theory, a question that you can ask about knots is whether they bound a disk in the D4. Yeah, so a knot bounds a smooth disk in 3 dimensions if and only if it's the unknot. But some knots bound disks in B4 and some don't. The ones that do are called slice. And people can tell whether many knots are slice or not, but this was one that defied resolution for a long time. Like people knew that it wasn't ribbon, so okay, so that's that. But a lot of invariants are 0 for it. So it looked like possibly it could be sliced. However, using Involutive Floer homology, they found a new method for obstructing sliceness, and this applies to this knot. So they show that this knot is not sliced. So this is work of Dye, Kang, Malik, Park, and Staffordgan. Okay, and the final applications, I want to talk a bit about stabilization numbers. So in dimension 4, we care a lot about exotic pairs. So these are manifolds that are homeomorphic but not diffeomorphic. They're the same topologically but not smoothly. And okay, so there is a theorem of Wall back from the 60s that even if you have two manifolds that are homeomorphic, even if they're not diffeomorphic, they will always become diffeomorphic after enough stabilizations. A stabilization is taking a connect sum with S2 times S2. And the same is true for 4 manifolds with boundary, if they have the same boundary, and they're homeomorphic. So then you can ask how many stabilizations do you need? Like what's the smallest case such that these are diffeomorphic? And in practice, for most exotic pairs that people have seen, you just need 1 stabilization. Like a lot of exotic pairs, they just pick, like especially for closed manifolds, you get them to be diffeomorphic after just 1 stabilization, and it was an open question whether this is true in general. Okay, so then at some point, Jianfeng found a counterexample in terms of diffeomorphisms. There's an analogous statement about diffeomorphisms instead of just structures on the manifolds. But it turns out to also be false for manifolds, at least for manifolds with boundary. So there is a theorem of Kang from 2022. He showed that there exist homeomorphic smooth manifolds with the same boundary, and they are very simple. In fact, they are contractible, but they have non-trivial boundary. The boundary is not S3, such that when you stabilize them 1, they are still not diffeomorphic. So they are not diffeomorphic originally, they're an exotic pair, and they stay exotic after 1 stabilization. So again, this was an application of Involutive Floer homology, something that came out of it. Yeah. Okay, so this is interesting because, well, the ordinary invariants of 4 manifolds with boundary, there were invariants from Seiberg-Witten and Heegaard Floer, and they vanish after taking connected sum with S2 times S2. But when you throw in the involution, the involutive invariants no longer vanish, and in fact, Kang showed that they can be used to distinguish these stabilizations. All right, so that's great. There are still 2 interesting open questions here. Okay, so he showed that the stabilization number is at least 2. Are there examples where the stabilization number is at least 3? We don't know. And also his examples were with boundary. Can you find examples for closed manifolds that stay exotic after 1 stabilization? So you need 2. Okay, so these are still open, and that's the end of my talk. Thank you.
Any questions?
So, which approach seems to be so where do you have the best hope to have combinatorial ways of detecting smooth structures on four manifolds?
Okay, well, there was a paper in February that did just that by Teo Ren and Mike Willis. So they used the Skane lasagna algebra from Hovanov homology, so a version of Hovanov homology for four manifolds with boundary, and they detected exactly smooth structures. Again, it's on manifolds with boundary, so we still don't have it for closed manifolds, but I think that's the most promising idea.
Willis and who else?
Ren.
Okay.
Ren is a grad student at Berkeley.
Yes, and one more question. What about partner moves in all categories? Non-smoothable, non-PL, and other manifolds. So other analogs of partner moves.
You mean for triangulations?
Yeah. So if we have something non-PL, and so do we have any moves to get invariants?
I mean, if you had invariants defined from triangulations, I mean, I think that's what Turaev-Viro did, right? For
partner.
No, but the invariants, yes.
Yes,
partner.
And if you have some crazy manifolds with crazy triangulations which are not PL.
Oh, which are not PL, that's the question. Oh, yes, I see. Yes. I see. But that would be just in dimension 5 or greater. That's when you have non-PL. So I don't know the answer, but I don't think it's super interesting because manifolds of dimension 5 are higher are less interesting. Yeah.
Any other questions? So
that's one question.
My question is the Yamu's method based on the modular space of the instant home?
Yes. Moduli spaces of instantons on the 3 manifold times R, basically. That's how you get Floer homology. Yeah.
Okay, thank you.
Any other questions?
Hello, Professor. I would like to know, since we have Hovanov homology is related to not Floer homology by some special sequence, I would like to know, do we have some relations between the involutive Heegaard Floer and Hovanov homology, or some generalization of Hovanov homology?
Yes,
thank you.
There was a recent paper by Melissa Zhang and Akram Ali Shahi, I think, where they showed that there's a spectral sequence from the Bar-Natan Hovanov homology to involutive. Sorry, but that's for the double branch cover. It's not for not Floer homology, but yes.
Excuse me, just on this topic, you had a paper with Williams where you used additional gradings, something like Z2. If we have Z2, then maybe it can be related to some involutions. I don't remember it exactly, but if we have additional gradings, it seems like some involutions.
I think that was in RP3. That was in RP3. Yes, for the. So there's Hovanov homology and not Floer homology in RP3. Yes. In that case, we don't know the spectral sequence. But.
Any other questions? If no, thanks, Professor Manolescu.